right, everyone, welcome back to part 2 of our lesson on series and parallel. So now we're going to show how we build a schematic of our modules in series parallel. And one thing I want to point out is note that we have our combiner box already wired to the inverter. So we can do this work safely. Even though we're wiring up our modules in series and parallel, there's no need to be doing any of this with live voltage other than the voltage of a module. But the modules have the safe quick connects, so you can build PV systems up to pretty high voltages in a very safe manner. So that's kind of what we're showing with the combiner box is already wired to that next component. So the electrician is not wiring anything with live voltage. Okay, so again, here we're going to build up this system. First, we make our series connections. Those are the positive to negative, positive to negative. We build up the system voltage. In this case, we have two PV source circuits of 3 modules each. And then we identify those open terminals. That's where we would have our home runs that would go back to that combiner box. And now we make that connection from our series strings to the combiner box. And inside that combiner box, once again, are the parallel connections. The negative from each of these source circuits gets paralleled on its own bus bar, just like the positives, the red conductors get paralleled on the positive bus bar. And so that PV source circuit is one series string of modules. So in this case, we actually have 2 PV source circuits. And then the PV output circuit is that circuit between the combiner box and the inverter. The PV output circuit is after any parallel connections. All right, so now we have a bigger system. We're going to look at the voltage and amperage. So here we're going to have 2 series strings of 6 modules each. And in the lower left, you see our module specifications. We're going to identify where we want our home runs to be connected. You can see the electrician will say has already wired the combiner box to the inverter, as indicated by the black and red on the right side of the slide. So now we can pull out our multimeter, and check for open circuit voltage. And here we have 6 modules in series, so the voltage for each one adds up, and our VOC for one module in this case is 39.5 volts. 39.5 times 6 modules in series gives us, bingo, 237 volts. And we're going to also measure that other string to make sure we did that one properly, and sure enough we have 237 volts there. So now we know we have an array VOC of 237 volts. So now we're gonna bring each source circuit into that combiner box, and you can see where now they get paralleled on the corresponding negative and positive bus bars. So now our system is operating, and we can check voltage of the system, and we see it has an operating VMP of 186 volts, and that would more than likely be 6 modules in series times their VMP, or 31 volts. So that's where we measure that VMP. And we can also measure current on our PV output circuit. Now remember, we have put these 2 source circuits in parallel, and now we go to measure the operating IMP, and we get 18.2 amps. This is with some assumptions, of course, that the temperature and irradiance are basically standard test conditions. But for our purposes, it shows how we can use the module specifications and our digital multimeter to confirm the voltage and current that we would expect to see, assuming we did everything correctly. All right, and now we're going to look at series and parallel applied, and in this case on the DC side. Now I'm going to introduce something about inverters, but we'll get more into that in the inverter lesson. But most inverters have what's called a DC voltage window and a power limit. A 5,000 watt inverter can't have too much more power than 5,000 watts put into it. We're going to get into that more in the inverter lesson later in this course. So for right now, we're going to look at the DC voltage window for an inverter. It's even on a label on the side of the inverter that would tell you its voltage windows. So what we do as designers is we build our PV source circuits in series, so we get a series string that falls within that maximum power point tracking voltage window of the inverter. Now you can see on our graph there we have our IV curve of one series string. Again, that could be called a PV source circuit as well. But there's our series string. I don't know how many modules are in series, but we've done it so we build up this much voltage. And remember, the maximum power point of the IV curve is right out there on the knee. It looks like it's about right in the center of this inverter's maximum power point tracking voltage range. So that's great. That's one series string. So now we add another series string. It's the exact same size and length. We add that to the first one, and we've doubled the amount of current. The voltage is the same. So we add this string in parallel to basically double the amount of power on this inverter. So remember, first we build the voltage up with our modules going in series, positive to negative, positive to negative. And then in this case, we add another series string that's the same length, the same number of modules as the first string, and we've doubled the amount of current, we've doubled the amount of power on that inverter. So again, this slide shows how we apply series and parallel on a typical PV system. And for some of you who are electricians familiar with the AC side of our circuits in our home and our businesses, you know that these AC loads, AC circuitry in the home are actually connected in parallel. And think about it, the voltage coming from the utility isn't changing. So all of our circuits in our home, each circuit has the same voltage, and it's the current that adds up to provide power to all of our loads in the home. There are no series connections on the AC side. So just be aware that in our homes, all of our circuits are in parallel. So we have an example here in the lower left. We have a branch circuit. Looks like there are 3 lights on this circuit. 120 volt AC appliance, and it draws half an amp. We could put our clamp meter right there. Bingo, we got our 0.5 amps. We can turn on another light bulb, and now those 2 circuits, the current adds up. So now we're seeing 1 amp, right? Because these are in parallel, the voltage remains the same and the current adds up. We turn on our third light bulb, now we see 1.5 amps on that circuit. We can see over Now on the right we have another circuit that has three more light bulbs, of which two are on. Now we're going up and measuring kind of the service entrance in this scenario, and we can measure our 2.5 amps that's being pulled from these five circuits. And of course, this is assuming there are no other loads on in the house. Yeah, we just have to note this is an assumption that there's nothing else on pulling power from the utility. In this case, we only have these five light bulbs on. That's why we're reading 2.5 amps on that black conductor. And another area we do parallel connections in the PV world is with microinverters. Again, by now you may have heard of microinverters. We're going to get more into them again in the inverter lesson to come a little bit later. But for our series and parallel connections, it's interesting to note that microinverters are connected in parallel. Basically because a microinverter has an AC output. In our schematic on the lower left, we have three modules connected to three individual microinverters, and each microinverter outputs more or less 240 volts and about 1 amp, right? So that entire circuit has the same AC voltage because it's matching that voltage coming from the utility. So the current from each microinverter gets added because these microinverters are connected in parallel. And I can confirm this. We can put my friend, the digital multimeter, around our inverter branch circuit, and all things being sunny, we would measure 3 amps going into that circuit breaker. So that's one interesting thing about microinverters is they are wired in parallel with the module and with each other. So, and this is how we see the importance of parallel connections with microinverters. And again, we'll get more into microinverters in the inverter lesson. All right, so our summary, what is a series connection? How does it affect the current and voltage output? What do we mean by a parallel connection, and how does that affect the current and voltage output of a circuit? And then what might be some of the limits to the number of modules wired in series and parallel? I mentioned the inverter voltage window and maybe inverter power limits. So yeah, what are some of the limits to the number of modules wired in series or parallel? And as always, we have some additional resources. Even though those are old home power issues, their articles on series and parallel are both really good, and I think they provide a lot of great information. So, all right, thanks for joining me on our lesson on series and parallel.